That's just great.
It's recording now. Please go ahead.
Good. Okay. Well, thank you, Mohammed. It's a great pleasure to have this platform in your very active math seminar series. I note from your website that my seminar is one of 8 this week in mathematics and one of 2 on numerical topics. And though your seminars start late for me, being 7 or 8 time zones to your east, I'm going to have to keep an eye on these virtualized seminars for those that I need to zoom into as audience. This is the 3rd time that I've had the honor of an NCSU numerical seminar, previously in November 1998 and November 2005. So that dates me, on both occasions in person, of course. NCSU has a very special place in my heart because of the outstanding dedicated SciAm service from its faculty. While I know Ilza, Tim, and Ralph in many technical contexts, I know them best from serving with them on SciAm councils, committees, and editorial boards. And Alina Chertok is another very dedicated servant of SciAm, just one I haven't served with yet. I have many other longtime colleagues on the faculty like Semyon, Jeff Scroggs, Mike Shearer, and Carl Meyer, so it's great to be back. Except that I approach today's topic with some trepidation because NCSU is holy ground when it comes to solvers for nonlinear systems because of nonlinear doctor in residence, Tim Kelly. I've learned an immense amount about nonlinear solvers from Tim, but still nowhere near enough. Therefore, Tim is expressly invited to chime in real time to augment or to correct any misimpressions that I may give to impressionable young scholars of numerical methods. And that way I'll learn something too. So I've chosen for my topic, nonlinear preconditioning for implicit solution of discretized PDEs. And I think you can see the shared screen, but I just have to begin noting that today is the Autumn Moon Festival. So I don't know how many Chinese, I don't see, oh yeah, I see at least one in the audience. And I greet you where it is already a very high and full moon. This is not my photograph. I don't have a camera this good, but I hope you'll have a good unclouded full moon for you tonight. The motivation for nonlinear preconditioning is nonlinear stiffness. If you Google nonlinear stiffness, you'll find about 190 results, but most of them are about materials science. But 12 out of the first 13 are to our papers. It's a term that we introduced in the year 2000. And if you Google, or if you go to Wikipedia and look up stiff equation, you'll find the linear origins of the concept of nonlinear stiffness. Stiffness is generally something that in an iterative, whether it's time stepping or solution methods that are iterative, that prevent you from taking as large a step as you would like to follow the phenomena of interest because of encountering a stability limitation. So it could be both positive and negative eigenvalues of very different sizes, fast reactions, slow reactions when you're interested in the slow. It's a concept that something is holding you back. And in the context of Newton's method, it's very often the case, as shown in this figure here, that any robustification for Newton, like line search or trust region, will damp the step back because of some small number of extremely fast-moving directions in the Jacobian, and may stretch you out on long plateaus. And this is, of course, whenever the boxed assumption, which if we set f of x to 0 gives us Newton's method, is not a good approximation to the full f of x. So strong nonlinearities in just a few components can result in a long plateau. And Newton methods may therefore waste considerable computational resources solving ill-conditioned large linear systems on each Newton correction when the Newton correction is then damped back to a very small amount. And examples of such things in the PDE context include shocks, combustion fronts, and recirculation bubbles. And there are other examples in solid mechanics, magnetohydrodynamics, and so forth. So a nonlinear preconditioner performs nonlinear relaxation within one or more subspaces inside an outer Newton accelerator on the full set of unknowns. And analogously to linear preconditioners, such as domain decomposition or multigrid, we put them inside an accelerator, and linearly preconditioned Krylov methods are often used inside both the nonlinear subproblems and the global Newton problem. So Jacobian free Newton Krylov, or just, other kinds of Newton Krylov solvers. A prime consideration in selecting a nonlinear preconditioner is whether the outer nonlinear problem that you get is amenable to further linear preconditioning on each Newton step. And the earliest nonlinear preconditioners that we worked with, called ASPIN and MSPIN, which I'll introduce later, they complicate the linear preconditioning of the global Newton iteration by replacing a typically sparse one coming from PDEs with a dense one. So right preconditioners, which came later, like Inexact Newton, Backtracking with Nonlinear Elimination, they retain the original Jacobian. And a new left preconditioner, which I'm going to introduce shortly, can also, by some manipulations, employ the original sparse Jacobian, with which we have lots of linear preconditioning experience. So I need to start by showing my co-authors for this suite of papers. Lulu on the left was a student of mine. Li Luo on the second from the right was a recent postdoc, and Zhao Xuan Cai was my very first postdoc back in 2002, and he is really the dean of nonlinear preconditioning. We wrote the ASPIN paper together at iCase, actually, back from like 2000 to 2002. And then that spawned a lot of other creativity by other people. And of course, many of you will recognize Rolf Krause, and some will recognize Fengying Huang, who have co-authored some of these papers. Now, I'm not going to give all the gory details. I'll defer a lot to the end because I mainly want to motivate and intrigue for the first half hour or so. So we'll illustrate nonlinear preconditioning on some rather standard, easy to describe, somewhat familiar 2D PDE models, even a 1D model, even an algebraic system to begin with. There are other applications that are more sophisticated, more satisfying, you could say. Two-phase porous media flows in 3D, arterial flows, reduced kinetics, combustion, and so forth. We will use simple discretizations, second-order finite differences, and a two-point upwinding from Boeing in the transonic potential examples. I won't go too much into the discretization. The interest is the algebraic nonlinear results. There are other discretizations that are more satisfying for many reasons pertaining to the PDE itself, namely discontinuous Galerkin. And since it's an algebraic method, it works very well in that context as well. We skip most derivations, but you can see the references. But I will go through a sample derivation on the error bounds for output functionals because it's recent and I hope insightful. So the granddaddy nonlinear solver, the practical one, is Inexact Newton with backtracking, where you aim to find a root of fx equals 0 in Rn through Newton's method, adding a step correction, a typically damped step correction, S super k at the kth iteration, where S satisfies the equation 2 for a sequence of etas. As k advances, eta is typically ramped down towards 0, Eisenstadt-Walker or some other way. If eta were exactly 0, you'd get Newton's method. You'd have to invert the Jacobian on the negative of the residual. But that's a lot of work for a linear solver. So we often start with etas that are quite rough, like 0.1, and crank them down towards 10 to the minus 8th or so. And then we damp the step by a traditional globalization technique like line search, where you try to minimize some scalar merit function along the n-dimensional line segment between your current point and where the full Newton step would take you. Now, as I said earlier, that process can be very slow. Left preconditioning solves an equivalent system in the sense of the same root by modifying the equations, the residuals, replacing them with other residuals. Right preconditioning tries to get you in a better starting guess for each outer Newton iteration by modifying the current guess by relaxing within a subspace. So there are many examples. ASPIN and MSPIN come from our group. RASPIN comes from the group of Martin Gander, Victorita Dolion, and so forth. Nonlinear elimination preconditioned Inexact Newton is a new one. The great German solid mechanics group under Axel Clavon does nonlinear FEDI-DP and BDDC. And there are many different variations. The PETSI group, Matt Nepley and so forth, have written a nice review paper in CISC on these methods. Here's an analogy, a little 2x2 analogy between linear and nonlinear preconditioning and left and right sided. So you're all familiar with linear preconditioning, which can be formally brought to bear by multiplying by an approximate inverse. That densifies everything, so you don't want to actually do that, but you apply those matrices successively to iterates in your Krylov method, for example. And the linear system is in effect changed, and you go for reducing the condition number. With right preconditioning, you modify the iterate before you apply the Krylov matrix, and then you unwind it at the end. With nonlinear preconditioning, left is quite analogous. You modify the residuals in some way by relaxing within a subspace, for example, like in domain decomposition or multigrid in the linear case, or some other sequential elimination. And the right preconditioning it's slightly deceptive to pose it in the same way, because it's not like we solve a system for y and then recover x by inverting g. Instead, we make some subspace iterations on x to get a better starting guess, y, and then we plug that into the original Newton system. And I like this paraphrase from the first sentence of Anna Karenina. All linear problems are alike, but each nonlinear problem is nonlinear in its own way. And as a result, there are a lot of heuristics for how you pick those subspaces for nonlinear elimination, whether it's just a small subspace, whether it's a sequence of non-overlapping subspaces, whether it's a sequence of overlapping subspaces like in a Schwartz method. There are many varieties. Let me start off with a simple 2x2 example that shows how powerful nonlinear elimination can be and how it works. So here is a 2x2 system in the coordinate plane. You can see a log of the merit function on the left. It's a very steep valley with those fifth powers in the first component. And if you just feed this to Newton's method with an initial guess at the point 2,2, relaxing to the root at 1,1, you will see that the first step is a big overshoot, sort of parallel to one of those valleys. And then it takes small steps down the valley, it overshoots the root and backs up. And this little 2x2 system takes 13 iterations with a backtracked inexact Newton. But if you eliminate within the subspace consisting of the first equation to get a new system, then it will get to the root in high precision in just 4 steps from the same starting point. And if you want to look at what that is before we introduce it more formally, there's the first original system on top, and we replace it with the system in line 7, which in effect gets rid of those fifth powers. The second equation was linear to begin with. The first equation is reduced, instead of in effect a 15th power for x2, it's just a cubic power for x2. And that system, when fed to a Newton method, converges much more quickly. And in this case, you can see how much better that system is. But how did we get it, and how would we get it more generally? And below there's a chart showing how that root is approached from 4 different starting guesses surrounding the point 1,1. And the 2,2 box is the worst for plain Newton. The 2,0 box isn't bad, compared to NEPIN for that point, but NEPIN beats them all. And so what is it? So we want to partition the original system into a good set and a bad set of equations, which are typically associated with points where unknowns or degrees of freedom are defined. And so those are the good and bad components. And the goal is to replace the bad system, FB equals 0, with a modified system, T sub B equals 0, where T sub B is implicitly defined by doing root finding using the first subsystem. So you see that first subsystem, it preserves the current estimate for the good components, but it drives the bad components towards a new place where the FB residuals go to 0. So it's Newton's method on a subsystem. And then you find that correction, and that correction is the new set of nonlinear residuals for those components. You can derive the Jacobian for that new system at the top, equation 9. And it turns out that it's a Jacobian block of the original unknowns with respect to that shifted unknown, XB minus TB, on the original Jacobian block. And therefore, the Newton correction can be defined as that Jacobian script times some D, Newton correction, on the modified right-hand side. And then you can actually multiply through by that DFB DUB inverse and move, eliminate the inverse, get in effect an identity that gives you back the original Jacobian on the left. And now you have a modified right-hand side, which is modified by the upper left block of the original Jacobian. So it's now something that exposes the original Jacobian to linear preconditioning on each step, but it really was left preconditioning. So here's the algorithm written out more procedurally. You solve the subspace problem, which defines TB. You set up a modified global residual with the upper left Jacobian block on TB. You solve inexactly for decay, and then you do a traditional globalization on that Newton step. It's very simple, really. You reuse most of the components of your original solver. Let's apply it first to a 1D example that generates a shock and see how much more effective it is, even in this simple case, than a full Newton method. So this is a second order ordinary differential equation value problem for the velocity potential phi of x. And AX here is a cross-sectional area of a converging diverging nozzle, and rho of the velocity at any point x is given by this formula. So rho is a uniquely defined function of the velocity at that point. The velocity is the gradient of the velocity potential, and the cross-sectional area is a symmetric parabola. And this is a classic test case for transonic potential. And you can see that if the right-hand boundary value is small enough, you just get an acceleration and a deceleration. But if it passes a critical value, you get an acceleration through the center of the duct, and then a shock, a super Mach number, Mach greater than 1, and then a shock back to a subsonic value. And that transitions the solution over a very narrow range. And there's a lot of nonlinearity going on right there. So Newton's method with incomplete with backtracking is shown by these dashed curves for a particular value of that shocked exit velocity and an increasing mesh resolution. And what you will see in this slide and the next is that, in effect, the Newton's method walks that shock one mesh point at a time per global Newton step. It's a real waste of a Newton step. You solve everywhere, but you only get one mesh point closer to locating the shock. And finally, once the shock is in the right place, Newton polishes it in one step. It's very trivial, final, quadratic convergence. The and this should say NEPIN, actually, not NEIMB, but we changed the name retroactively.
David,
but
are you going to tell us what T sub B is for this problem?
What is
T sub B? No, for the duct problem.
You mean? I'm not sure what P is.
No, T sub.
Oh, T
B.
sub B. Oh, yeah. Oh, actually, well, T sub. Yes, I am. Yes.
Okay, fine.
Yeah. I know it's a little bit out of order, but I believe in intriguing, and then people are willing to put up with that, right? Yes. Thank you, Tim. Very. You're anticipating the next slide. What you can see on the right is for the 128 case, the convergence history for this blue curve here, which goes up to 56 steps before it sharpens the shock. So the first step, is flat. The second step is lazy, and it sharpens and moves out of the center of the duct, and finally, converges dramatically as Newton promises. So now we have to see what those equations are and where the bad unknowns come from. So this is just that 3-point finite difference discretization of the 2.1 boundary value problem. And rho tilde is rho itself for most of the domain, but for a subset of points where this adjustment parameter mu is other than 0, that happens when the local Mach number is greater than some critical Mach number. And then this coefficient here becomes positive and gives you, some rho upwinding. And we set this sort of clustering of bad points around the higher Mach number values as any mesh point where the local Mach number is greater than about 0.45. So the critical Mach number is 1. So any points that are sort of, near the height of this thing will be designated as bad points. And then T sub B will be the correction to the problem if you fix the points outside of that central subinterval and just solve Newton's method on the reduced domain 2-point value problem. Then that becomes the upper block of the equations. And that's what leads to this improved convergence of less than 10 iterations for all mesh sizes. Now, so that's the identification of the bad points for this example. And a very similar example, extending the same transonic potential flow here in 2 dimensions around the cross section of a traditional airfoil, which is shown here. This is a classic Boeing example that we did with David Young back around 2001. And here's the 5-point star generalization of that, little 3-point discretization in 1D. And here are the upwind values for rho in the case where the velocity is greater than or less than 0 at that point. And here's a similar switching function towards introducing any upwinding, but now, of course, we'll do it in both I and J.
Hey, David.
Yes.
Does using the local Mach number make the problem non-differentiable?
We use numerical derivatives, but yes, in fact, that you can even lose ellipticity in this equation when there are values of the local velocity that are high enough that you can actually lose ellipticity in this. And I believe it does make it, functionally non-differentiable in the sense that, in the continuous idealized limit, you have a discontinuity in the density. So yes, but numerically, you can plow through it as often we do with finite differences. So another good question. For the airfoil itself, which happens in the middle third of this interval, you can see the isomach lines And some of them in the dark, in the yellow and orange, are a little region in the forewing greater than 1, where the flow accelerates and then shocks down mid-wing. So this is just the middle third of this 2D picture. And this is just showing the pressure coefficient over that. And the difference between the upper and lower pressure coefficients is what gives you lift. So you'd rather not suffer this shock, which sort of takes away some of your lift. These are negative values of the pressure on the upper surface. So, this is, what aerodynamic designers like to work on. But what we care about is Newton's method. We care about the algebra of it. And this is a succession of pictures for the global Newton step 2, 4, and 7, showing a slightly increasing subdomain where we do that pre-elimination to replace the bad residuals with the Newton correction residuals. And there's a lot of points in this because this is a 512 by 512 mesh. It's not adaptively refined in any sophisticated way. It's a brute force Cartesian mesh. And you can see there's, even for these small regions, there's, 25,000 degrees of freedom. So it's not a small Newton problem, but it's an easy to converge one. And, because we're sort of freezing the Dirichlet values in an innocent exterior, and we're making efficient use of each step in the inner rather than dragging all these other things around with it in a linearly ill-conditioned global Newton correction. So here is a similar plot to the 1D. The red ones are unadorned INB, inexact Newton with backtracking, and the blue ones are, less than 10 iterations. And here is the unadorned convergence, moving the shock one mesh point at a time, roughly, and the very fast, getting into the convergence domain for the NEPIN. And on the left, you can see why we go to such fine meshes. We are continuing to improve the solution as the shock sharpens, as it takes advantage of narrower and narrower subintervals to approach that idealized discontinuity. But most of the benefit of computing the integrated lift is realized much earlier. But here is another interesting, well, in the sense that this is a heuristic identification of bad points. This shows that as you vary the cutoff Mach number that defines that blue domain in the previous example, you do get a varying number of global Newton steps. So there is an advantage to being as clever as you can be, maybe from machine learning or something, as time goes on, to pick a good cutoff point. So that was NEPIN, which is the most recent and in some sense the method I like the most. And we're half an hour into the talk, but let me tell you about another method that we like, which for a different purpose, which is called MSPIN. And MSPIN is a multiplicative version of the additive ASPIN. So it's the Gauss-Seidel to the Jacobi ASPIN, if you like the nonlinear analogies. So let me start with ASPIN, which was originally a domain decomposition method, and then generalized to a field decomposition method. And then we realized that for fields, it's not very good, but we like the Gauss-Seidel version for fields. And indeed, many people beat us to that. For example, the IMPES method in subsurface flow is in some sense a Gauss-Seidel nonlinear elimination method. It just failed to get wrapped with the outer Newton method that it serves as a good preconditioner too. But we can generalize that class of methods from a fully defined nonlinear algebraic system. So here's ASPIN. You divide up a global domain into subdomains. They can be overlapping. And you define these sort of projection operators into subdomains by defining subspaces as a subdomain outside of which everything is zero. So VI is the set of non-zero mesh points here when all these are zero. And so you can define a residual that maps the full space to a subspace in effect in this way. And then the modified ASPIN is a sum of these T's, these solutions in each subspace, where the Dirichlet homogeneous boundary values encroach right up to the edge of the subdomain. Then you solve in that subdomain and you sum up those corrections, which will have some non-zero overlap, and that is the new F. Now, you'll quickly realize that this F has a dense Jacobian because, these subspaces are non-zero in their, these corrections are non-zero in their subspace, and we're summing them up to cover all subspaces. So as nice as this is for Newton's method, it doesn't help you much in solving the global Newton correction equations. Now, it does do some linear preconditioning along the way, but then you're stuck with whatever you've got. The field split ASPIN, which we can demonstrate by a 2x2 system, says, these could be two non-overlapping subdomains. They could be two components of a PDE system. But let's call them U and V for the components and G and H for the residuals. And they are defined implicitly, the corrections that is, by eliminating within subspace for U and then eliminating at the same time. So, you fix V, eliminate for U, fix U, eliminate for V, and then find those two corrections, and that defines the new residual. And those are also dense in their Jacobian. Now, we showed in the original ASPIN paper that if F is just a linear system, partitioned thusly into two subsystems, that you get additive Schwartz. So, it does the right thing, or you get block Jacobi if they don't overlap. ASPIN does the right thing if F is linear. Of course, if F is linear, we're not stupid enough to pre-multiply by M inverse, like we're doing in the nonlinear case. We would use M inverse as a preconditioner within a Krylov method. But it's a simple, block preconditioner. And that gives you a hint that it's not going to scale to a huge number of parallelly independent subdomains, just as block Jacobi, will eventually deteriorate in its condition number by leaving off all of the off-diagonal couples. But this can then be generalized to a nonlinear Gauss-Seidel, where the second correction, the H correction for V, starts with a corrected version of U already. And this turns out, just as with Jacobi over Gauss-Seidel over Jacobi, to generally be a much better iterative method. It's by appearance a much less parallel method, because we do these two steps sequentially. But each of these steps could be a very big, PDE in a system of PDEs. So it's still, we got a lot of concurrency to work with. And in the MSPIN paper, which was the PhD thesis of Lulu Liu, she derives the corresponding script Jacobian. It's defined with respect to derivatives of these shifted arguments, which makes it rather hard to compute. But in practice, since these shifted arguments approach zero as you approach the root, you can sort of cripple an already inexact Newton method by evaluating with respect to the block components of the original. And you can generalize this this triangular solve to three or more components without any difficulty other than, the subscripting and so forth. So let's take an example. This is a three-component problem in a 2D driven cavity. It's called the vorticity velocity formulation of the driven cavity. You have the Laplacian of U on the y vorticity gradient and the Laplacian of the vertical velocity sourced by the x vorticity gradient. And the vorticity, this is really the momentum equation, with cross differentiated and subtracted to get the vorticity. It is a nonlinear equation because it involves the velocities multiplied by vorticity gradient. This is the transport, this is the diffusion for the vorticity equation. And these are in some sense the resulting continuity equations for defining U and V. The Reynolds number controls the nonlinearity. When U and V are large, this nonlinear term, this quadratic nonlinear term dominates. But these two equations are linear. So just as with our original 2x2 algebraic problem, it pays to fork off, the linear problem from the nonlinear. And I like to show the results first. What do you get if you do that? Here is that driven cavity problem with which I began the lecture. This is Reynolds number 1, Reynolds number 100, Reynolds number 1,000, Reynolds number 10,000, global Newton with backtracking. It will take forever to get these guys into their convergence domain. There's sort of a critical Reynolds number, which is 769, where Newton, nicely turns over and finds its quadratic domain. And, slightly above this, it will look like it's going to go forever. Now, let's not take these Reynolds numbers too seriously in terms of the fluid mechanics modeling. There's a lot of artificial diffusion in the discretization of this problem. It's only on a 128 mesh. But the point is, it's making the nonlinear problem much harder by boosting the coefficient of the quadratic terms. So this is an algebraic example with a fluids-like motivation. And this is ASPIN with a 4x4 domain decomposition at all Reynolds numbers. It kills the problem. This is MSPIN on a field splitting. It kills the problem, always within 10 iterations compared to, a more or less indefinite number. So, this additive method with complete parallelism on each subdomain, this multiplicative method with sequential between the fields, but parallel within a subdomain, they both make, a lot of good sense. Before algorithmically defining MSPIN, just assure you that, we have expected results. The roots of the original and the modified system are equivalent in this, in the sense, they have the same solution in a neighborhood of the physically realistic root. The forward is easy. If you had a root of f, then the Newton corrections in each subproblem are going to be 0. So the nonlinear residual is also 0 in the modified form. The reverse is proved by noting that the Jacobian is non-singular in the vicinity of the solution. Hengbin An was courteous enough back in 2005, following the original ASPIN paper, which showed nothing about convergence rates, to show that it is superlinear if the forcing tolerance approaches 0, and quadratically so if it approaches it as fast as the modified residuals. And Lulu, who is not scared of analysis, proved that for her own algorithm, got those same results. So let's talk about nonlinear preconditioning. And when I get to the error bounds, you'll see, the MSPIN formulation for that. So this is a recent addition done in collaboration with Rolf Krause and Lulu, noting that by the time you get close to the solution of the nonlinearly preconditioned problem, you're actually close. You're getting within the ball of convergence of Newton. So why do the extra work? So it's a very simple algorithmic, efficiency adaptation. The preconditioned steps are intrinsically more expensive because of the subproblems. You should turn them off. And a pretty good way to turn them off is when this ratio between the agreement of the local linear model and F itself, this is the residual at the next step. This is the difference between, the current residual and this thing, this Newton residual. When that is small enough, you might as well switch to plain INB. It's cheaper. And this very simple switching works well. And looking at this problem that we just looked at more generally, these are different Reynolds numbers for inexact Newton with backtracking, full MSPIN with all eliminations, and MSPIN adapting to INB in the terminal iterations. The full Newton doesn't converge for any high Reynolds numbers. MSPIN and MSPIN adapt give you the same outer convergence. And if you put your microscope on what's happening inside, you always get a win from the adaptive version. In Reynolds number 100 and in Reynolds number 10,000, you actually save 2 terminal iterations. For Reynolds number 1,000, you happened to save 1. So that's a simple switch. Another cool thing, fairly recent, is approximate error bounds on some linear functionals of what you're solving the PDE for. So I think, yeah, I have 15 minutes left. I can at least go through this one, and then we can choose what to leave out or stop for questions. Often in applications, it's overkill to find the PDE solution to high accuracy everywhere in some norm. Often we just need some linear functional of the solution, some integral of gradients along a boundary, which gives us a flux, some maximum value or value at a point, or average over a subdomain. Often those integral functionals of the solution of the PDE are all we need. And in such a case, since they're integral functionals, often you get them before you resolve the solution of the PDE to the same accuracy. So here's an example, for instance, within semiconductor cooling. Let's say these are some chips, and this is a fluid or air being blown over the chips with some cold ambient. And what you really want is the heat flux, over the surface of the chips. It's nice to know the solution everywhere, the temperature everywhere, the velocity everywhere, the pressure everywhere. But you'd be happier with less. With sort of what's the mean temperature? Is it below some threshold at the chip? Am I blowing hard enough for that? So here's our MSPIN with the G and the H, the corrected. No, these are the original. Yeah, these are the original 2 primitively defined residuals, and the original values U and V that we seek. And so we're going to define, a linear functional. We'll look at a few examples where the U's are inner producted with some phi1 and the V's with some phi2. Could be, again, an integral picking out a point in a characteristic function or whatever. So these size could be sparse or dense or some coefficients of a quadrature rule or whatever. So we can derive the difference between the actual linear functional that we want and the linear functional at the kth iteration of the MSPIN preconditioned nonlinear system by basically, taking the inner product of this difference and the inner product of this difference. And the punchline is that you can relate this desired quantity that says how close you are at the kth iteration to what you want to get to some residuals of the modified values at the kth iteration and some component blocks of the 2x2 Jacobian. And CK here is a sure complement with respect to the second. No, sorry, it's not a sure complement. It's this block product, this conformally blocked product of what could be an unequally diagonally blocked. No, sorry, yeah. These blocks are square, right? And these could be rectangular to map between them. So let's review MSPIN. The modified residuals are little g and little h, defined in this Gauss-Seidel way. The script B is this set of Jacobian blocks, which will give this shorthand. And if you go to the paper, you will see that dg du is just an identity matrix. In fact, that's very clear to see right here. dg dv ends up being B inverse on B12. dh du is 0, and dh dv is this combination. And so we can note that G and H are expressible as the residuals at the kth iteration here, and some other terms relating to these differences and some high order terms. And discarding the high order terms gives a 2x2 system for the deltas in terms of the nonlinear residuals as the right-hand side and the matrix blocks as, the little 2x2 matrix. So the solution for that is, the differences of what you want and what you've got at the kth iteration related to the readily evaluated residuals of those components at the kth iteration. And so you can actually bound the delta LK, where K can be 1 or 2, this K is the top block or the bottom block. In terms of these norms, this absolute value or these norms. So I'll leave that to the paper for details, but you get a nice flavor.
Excuse me, David. So sorry.
Yeah.
You have. So here I'm a linear algebra person looking at an inverse, right? So C2K is the norm. When it's less than 1, the inverse exists. But even if the norm isn't less than 1, I guess you guys found it still exists then.
Let's see. Yes, the inverse. Well, I'm having to confess to
I guess so. We're probably all these things are okay, fine.
You can derive CK inverse from here. So since B1 and B2 are invertible,
and I see that if you have the norm less than 1, you do the Neumann
that's
thing.
right.
The nice idea.
Yeah, that's right. So it's convenient if that's less than 1, but if not, you at least have something. Yes.
Thanks for clarifying.
Thank you, Ilse, for that's actually the key point of this slide and going from here to here. And I was gonna miss noting it. So let's apply this to our previous problem, which is this subset here. But now we have an energy equation. We have heat diffusion and heat convection, which is modified. The nonlinear terms are modified by a Prandtl number, a scalar which gets large if you have a small diffusion for temperature. And this is a Grashof number, which gives you a buoyancy term, which is your driving term for the vorticity equation. So the momentum of the fluid is driven by a temperature gradient. This is if there's any fluid mechanics people in the audience, you'll grant me these equations. They're a nice model system with quadratic nonlinearities and a little bit of intricate coupling. And we'll partition the fluid part and the thermal part in making our G and V. Or we could actually do a three-way thing with the linear part, the vorticity part, and the thermal part. But these are some sample linear functionals that we can solve for exactly, tracking an exact solution, and then estimate by our bounds approximately, and therefore evaluate how good those bounds are. So one of them is an integral along one of the borders of the domain. It's an integral along the midpoint of the domain of the u velocity. So it's in some sense a measure of how much flux there is at that vertical midpoint. This is a pointwise value of a velocity gradient. This is a pointwise value of the vorticity, and this is an area average of the temperature. And in this picture, the solid curves are the actual results. So this is that area, this is that line integral, this is that area average, and these are those two midpoint values of the V gradient and the vorticity. And the solids are those actual values. They're converging nicely as the iterations advance at 3 different Grashof numbers. That measures the magnitude of the forcing of the residual. Prandtl is fixed and Grashof is increasing, making the problem more nonlinear, more difficult as Grashof increases from red to blue to pink. What's interesting is to look at the dashed curves. Those are the theoretical bounds on the quantities that are being exactly evaluated at every iterative step. And indeed, they are always above the actual value. This one's really very nice. This is that area average that is very well approximated by the, in fact, all of these area averages do well asymptotically, better than the other kinds of functionals. But you can see that if you only needed a certain accuracy, you could stop, some number of iterations earlier, or at least be confident, that you were stopping at a good spot. So that's I think, a collection of illustrations of possible uses for nonlinear preconditioning, defined algorithmically, illustrated by some simple examples, and some flavor of the relative. I mean, this is not deep, numerical analysis in terms of showing, what proofs we have. Now, I know that NCSU is big on subsurface flows. So all I'll do here is show a movie of the fact that, yes, we have started to apply this to some more interesting problems. So here is the velocity saturation subsystem for Darcy and the saturation equation for a wetted and a non-wetted phase, two phases in a reservoir, with all of the complexities of capillary pressure and high inhomogeneity in the porosity and the permeability. So these are hard problems for Newton. They have bad linear systems in Newton, and you want to reduce the amount of Newton work. And yes, you could use one of those methods like IMPEs, where you do sort of an implicit pressure and an explicit update of the saturations. But we like to go fully implicit. Tim likes that too. So we use backward Euler and we throw all the unknowns into a global Newton method at every time step. But we like to be smart to component segregate the nonlinear preconditioning for those fully implicit problems. So that's the theme here. We do go to a respectable discretization method, namely Galerkin, the discontinuous Galerkin, for all of its usual benefits in terms of the element-wise conservation at the top, the good parallel efficiency by a thin halo at the bottom, the ability to do adaptivity, control diffusion, capture discontinuities, etc. So here is yet another flavor of nonlinear elimination. This is one where you modify the right-hand side and don't try to throw anything back to the left. You just do a correction for every right-hand side by nonlinear iterating inside a subspace before you apply full Newton to the modified starting guess for each space. And we do this in two different ways. This is the good-bad decomposition. The better way is to find bad points by looking for large residuals. So, in those original discretizations, look for the large residuals and call those the bad points. Another thing you can do is to break it down by fields, like we did for the driven cavity, and eliminate certain fields. So I'm only showing a movie here. Here's a 2D problem. This is log permeability. This is log porosity and log permeability. Absolute porosity between 0 and 1, and log permeability. And these are some solutions with homogeneous and heterogeneous permeabilities with 0 capillary pressure, very smooth, high capillary pressure, fingerings and so forth. If you turn on any capillary pressure, Newton just won't converge for you. All the backtracking in the world. But if you eliminate high residual areas, you can get Newton to converge on these harder problems. And ultimately you do win in CPU time, not by much. I think of this as a robustification. This is a column of CPU times. Where Newton converges, it's not much more expensive. But of course, if it doesn't converge at all, then the robustness advantages are there. These are showing, how many sub-iterations of Newton are happening and how many linear iterations are happening for the elimination steps. This is the results for different time steps in these successive curves of the same color, and these are the different elimination strategies for high residual or multiplicative. This shows you that you can quickly go to full Newton steps if you do the nonlinear elimination. So this is step length 1, no damping. And this shows you some example bad subsets. So, they're not simply connected domains, they're subsets of the general nonlinear set of equations. Now, when we solve these, we're not being clever in terms of parallel or even sequential performance. We're just zeroing out or diagonalizing the other unknowns to eliminate this subset. So it's not an efficient implementation, but it just shows the robustness. This is before and after elimination for some different problem. Before and after. This is the guess that you throw to Newton rather than throwing the full mess where this particular residual is going to damp you back and maybe not allow you to converge. The last example is SPE10, the famous reservoir model. And here again, regular Newton and Newton with these two strategies. And this is actually a scalability example, a strong scaling for a successive number of processor doublings. Not great, but not well implemented yet. So nonlinear preconditioners, they can be effective, especially by robustifying Newton. And when they do, as you saw in the last example, they often obviate other globalization methods like line search, although we still want to always use those as a guard. It does expend extra computational cost, but the main advantage is it reduces the number of outer methods on the full problem with all of their synchronization issues in the Krylov solver and so forth. You can adaptively get rid of some nonlinear iteration, and you can maybe take advantage of some bounds. There's a lot left to do, and I commend this fun, area. Very heuristic, very intuitive, but probably you can do more theory, to some NCSU grad students. But there are also some algorithmic things that we'd like to look at. In terms of implementation, because of all the poor load balances in the adaptive subproblem selection, we'd like to go to dynamic runtime systems in the parallel implementation. Some outer iteration work can be done while some inner iteration work is still being converged. Or we could even think of asynchronous nonlinear iterations. That's been a revival in linear iterations with high concurrency and ill-behaving cores. It certainly is invited here. And then, of course, there's all the heuristics of picking bad components. That was Tim's first question. That was a Mach number cutoff. It could be a residual magnitude cutoff. It could be a gradient of the solution cutoff. One idea that has proved effective is sort of cascadic. You have that tuning parameter and you keep cranking it out. And so originally you're doing a small number of unknowns, and then you're gradually doing more and more until you have enough eliminated to just go to full Newton. And I strongly believe that machine learning will be the best thing to do here. And with that, I thank you. I've used more time than I rehearsed, but I get drawn out, well, you have the recording, but I'm happy to hang around for questions, and I see already two, so that's good.
Thank you very much, David. I guess we're over time, but I guess we can stick around for a couple.
But whether the recording is good or not, I'm happy to look at questions.
Yep.
May I ask a question?
Please, Ilse.
So I'm bugging you again about good and bad components, David.
Yeah,
So
yeah.
the bad components, are they determined by physics, or is that more an algorithmic thing?
Okay,
I'm
so
asking about intuition.
Yeah, so I said that every nonlinear problem is nonlinear in its own way. And so it's I believe that there are going to be ways of learning bad components. One fairly good general purpose way is to just look for the high residuals. You go back to Southwell relaxation. Where are the residuals big? Start there.
An algorithmic thing then.
Yeah, that's an algorithmic thing. But, for the first one, it was a physics thing, where is the Mach number too high? For the last one, it was a combination of, what fields are harder versus, it's like IMPY's intuition for the subsurface modelers. So it's really the Wild West, and have some fun, be clever. But that is the hard part. That is why there's not really good software for this yet, for general purpose software. Two reasons. One, it's not easy to get load balance subproblems. Two, it's not easy to sort of prescribe fail-safe bad points.
So as somebody who is ignorant of anything and everything nonlinear, I really appreciated that you made that correspondence between linear and nonlinear methods, the left-right preconditioning, Gauss-Seidel and Jacobi. That really helped me. Thank you so much.
Good. Yeah, there's
this. That one,
yeah. Yeah, and then there's well, of course, nonlinear Gauss-Seidel and Jacobi have always been there, but within the context of what you're doing on those subsystems. Yeah, thank you. I'm glad that's useful. Yeah.
Any other questions?
Maybe all the questions were
maybe
about
I ask a naive question. I worked on a field in fluid dynamics called exact coherence structures. I don't know if you've heard of this, but basically it's finding periodic orbits in the turbulent tractor. Okay. And that can be written as an elaborate root finding problem, basically.
In fact, you mean where you're subtracting, where you have a propagator and you subtract the propagation at the end of the period from the initial state?
Exactly, yeah.
And then that gives you a dense Jacobian, doesn't it?
Yeah, it does,
yes.
Yeah.
Yes, I love that problem. I didn't know you were working on it, but I want to follow up on your contributions now because I love that problem.
Yeah,
it's a good problem for Jacobian-free methods, right? Because the Jacobian is hard to compute.
Oh yeah, you have to use GMRes or something like that. But then the crucial step I found from experience is that the hook step. I don't know if you're familiar with this GMRes hook step. I don't know if you've.
I don't think I am.
Yeah, all right. We can maybe talk about this.
Okay, but that periodic root finding problem. By the way, do you know your period? Or do you have to find out?
No, that's one of the unknowns.
Yeah, okay, so that makes it even harder.
Yeah.
In fact, probably much harder, right?
Yeah.
But maybe since you have, maybe that would be, I don't know if that would be a good nonlinear elimination, decomposition. The period is just one unknown compared to all the others. I don't know whether that may or may not be, fix all the others and try to root find the period and then that steps you.
The problem is you don't know the others either.
Yeah, right. But I mean, but it's a bootstrapping thing. But maybe there are partitions of the global system that could be nonlinearly subsolved.
I would love to talk more about this.
Yeah. Anyway, if you point me to a reference, maybe we can work on that. I won't have any more intuition than you. But maybe our students can get together and take it one step further. Yeah. Good. Well, then this was very productive for me to think about that context.
All right, good.
Great talk, David. Great talk.
Great talk. Thank you very much, Ken.
Thank you very much for, again, this honor for